All right, 3.4, continuity and one-sided limits. And so we should start with defining what continuity is. And the function f, right here, the function f is continuous at c if three things need to happen. One, f of c is defined. Okay, so if you plug in that c value into the function and you get out a number, hey, it's defined, you pass step one of the continuity test. 2, limit as x approaches c of f of x exists. So if the limit exists, you pass step 2. Yay. And 3, limit as x approaches c of f of x needs to equal f of c. So pretty much 1 and 2 need to equal the same thing. If 1 and 2 equal the same thing, and they're both not, the same thing isn't undefined, then guess what? You're continuous. Woohoo! There are 2 types of discontinuities that you will see at some point, and you probably already have seen, we're just not in terms of limits. One's removable. Removable discontinuity. We have a coordinate plane, and we have this function. It stops, keeps going. That little stop point right there, whatever this we want to call that, that's removable. Okay, and then there's non-removable. A non-removable is when we have jumps, right? Let's do that, and close circle there, and then it starts back up right here. So that would be a non-removable when we see a jump. Or it could be infinite, like one of these. That would also be non-removable. All right, so let's find the continuity of these 2 functions. So if we were to graph this first one, I'm going to graph it in red. It would look like the function x plus 1, because if I were to factor the numerator there, it would be x plus 1 times x minus 1, and the x minus 1s will cancel. Cross out, and it'll be like x plus 1. So if I were to graph this, I have a point there, and we'd have an open circle at 1, 2. Why? Because 1 makes numerator and denominator 0. So we will have a removable discontinuity. So if we are talking about the discontinuity of this function, we will say that at x equal to 1, it is discontinuous because of a removable discontinuity at x equal to 1. So it can be continuous at every value within its domain except x equal to 1. X equal to 1 is not in your domain. This second one here, this f of x here, we'll use green for this one. This will be interesting because it's a piecewise function, which means we should watch out for the possibility of a jump. So the top function, when x is less than or equal to 0, we put 0 in, the output's 1, and then the slope's 1, so every time we go down 1, you go to left 1, so it'd be like that. And then it's going at x squared plus 1 is when it's greater than 0, so put 0 in, your output's 1, so it's going to do something like that. There's such a thing as one-sided limits, where this to the left right here, I should have made it to the right because it's this is a limit coming from the right with a plus on top, and the limit comes from the left. That's when we're just analyzing if it's coming from the right, if it's coming from the left. If I'm asking for this, you're just, and I give you a graph of this, so you have this graph, just making one up here, and I asked you for the limit coming from the right, your answer would be whatever this dot would be right here, okay? It's coming from the right. Now if it's coming from the left, it'd be whatever this value would be, because it's coming from the left and closer to whatever this value is, okay? So it'd be 2 different values come from the left and from the right, which we will define in a moment. but from right, this would equal this, left equal this. All right, so the existence of a limit. Let's let f be a function, and c and capital L be real numbers. Real numbers. The limit of f of x as x approaches c is L if and only if limit from the left as x approaches c of f of x equals L, and a limit from the right as x approaches c of f of x is L. So what this is saying is pretty much what you did in the last section, right? We look at the left side and we look at the right side. If they equal the same thing, you have a limit. They must be equal to the same thing in order for the limit to exist. So this is continuity of a closed interval. This is closed because it's not all real numbers for your domain. Your domain is going to be between -2 and 2, and including those values. If it's anything more than 2, you'll get a square root of a negative number. If it's anything less than -2, then it's going to be square root of a negative number again. So that must be in between and including that, because you can't find the square root of 0. So, with that in mind, what we need to do, let's find the continuity of this, of the closed interval. So the left side of the interval is -2. So I'm going to check that from the right. And then I'm going to check from the left of the end from the right. So if I find each of these individually, I call this f of x, I would end up getting 0 for each of them respectively, right? And I just drew the graph on the right here, and since it's clearly continuous in between, and it goes to a value coming from the right and then coming from the left here, we can conclude it as continuous on this whole interval. Alright, so some properties of continuity, just to rattle off. You know a function is continuous. If you do certain things to these limits, you can still say that they're continuous. So let's let b be a real number, and f and g are continuous at x equal to c. Then we can establish the following are continuous. Similar to what we did earlier, scalar multiple. So we can just simply take that b and multiply it by the function. Sum or difference. Add or subtract two functions. Still be continuous. Product. You multiply two continuous functions, and it'll still be continuous. Or the quotient. Which is just simply two functions divided by each other, as long as the denominator is not equal to 0. Whatever, as long as that doesn't happen, you're still good. All right, intermediate value theorem. So this is the last thing we'll do with the section. So let's say we have f is continuous. I'll abbreviate continuous on the closed interval a to b. And f of a does not equal f of b. And we have some number k between f of a and f of b. Then there is at least one number c in the interval a comma b such that f of c equals k. All right? So let's do an example of this real quick. If we have f of x equals x cubed plus x minus 1, and we want to use the intermediate value theorem to approximate the zero of the function on the interval of 0 to 1, let's try that out. So if we put 0 in the find f of 0, it's going to be negative 1. And if I find f of 1, it will be equal to 1. So what does that tell us? Since 0 is in between negative 1 and 1, therefore it must mean there is some number between 0 and 1 that gets us an output of 0. Okay? So, thanks for watching, and we'll see you later.